Hi everybody, this is part B of the videos, and I just had them split up so we can focus on two different concepts here. So in part A, you focused on the reaction quotient Q, which is a ratio at any point in a reaction. Here we're going to focus on solving complex equilibrium problems. So as a quick recap, we usually have some kind of data about a reaction and the value K. Now, in many problems involving equilibrium, we use an ice table to determine what the concentrations are. If we can't, we combine that with K and use an algebraic expression to determine what X is, and then sub that back in. So these are kind of the steps that we followed throughout the unit so far, and now we're just going to start to apply them. So in some cases, we haven't encountered it too often yet, but we'll get a polynomial when we try to simplify, and there's no way of squaring or kind of assuming out of an exponent in the equilibrium expression. So what we're left with is a quadratic equation, and you'll notice that because you'll see a term x squared and x separately, which you might have trouble factoring out given the numbers that we're using. So what we can do is rearrange this into the quadratic equation in the form ax squared plus bx plus c equals 0, so move everything over to one side, and then we'll solve for x using the quadratic equation. That x can be substituted back in, so it's a lengthy process, but it does work mathematically, and it allows us to determine equilibrium concentrations. Now, a lot of times this will be done by sensors and spreadsheets automatically, but it's important for us to understand where the values are coming from, because if we go into this kind of work, it's up to us to program the sensors for the scenario that we're using. So we'll look at an example here, okay, where we apply the quadratic, and you'll see how it comes about. So what amount of hydrogen iodide is present at equilibrium given the following conditions? And I'm using hydrogen iodide here, not hydroiodic acid, because it's a gas. For it to be an acid, it would have to have aqueous beside it. So because the question is very straightforward, what amount is present at equilibrium? So this tells us right off the bat, use an ice table. So let's use the setup that we have here. We'll go I, C, and E, because the ice table helps us to see where the values we have. So we're working with a 0.5 liter container, and we're told that there's 1 mole of hydrogen. Sorry, we've got 2 moles of hydrogen and 1 mole of iodine. So their concentrations need to be divided by half. Remember that concentration equals the number of moles divided by volume. So for hydrogen, 2 divided by 0.5 is 4. I'll just put that here without the units, and this will be 1. So dividing by 0.5 is like multiplying by 2. We have no product initially present. Right, so if we're comfortable setting up ice tables, we know that we lose reactants, and we gain products. Right, we're not told any other information except what the K value is. So in the end, we're left with an algebraic expression for our equilibrium row. Now, because we can't solve this, right, what we've done before is sub into K and solve for X. Right, sometimes we'll be given information to solve for X directly, and we'll do that. So let's set up our K expression here. And remember, this is different than Q because we're being told it is at equilibrium. And that's why I'm not using the Q expression. So we have our products over our reactants here. They're all gases, so they all get included. Okay, we'll substitute in the fact that we know K is 50. We're going to have 4 minus x squared divided by 2 minus x. I just plugged in the wrong number here. We have 2x squared. There we go. Times 4 minus x times 2 minus x. All right, so understand where those values come from in this scenario. So as we go through here, our answer is simple. If you're given this in math, your object would be simplify and solve for x. So we have a couple of options here. We can't square root anything like we did last time because there's no squared term in the denominator. So what we have to do is expand out. So we have 50 is equal to, don't forget that this applies to the constant and the variable. So we've got 4x squared, very common mistake to forget to square the first part. And then when you multiply those two binomials, you'll get 8, take away 6x plus x squared, right? And I've just simplified that out without showing all the steps, just for ease. But remember, FOIL, right? Multiply these two together, and then add like terms. Okay, so that should be something you're comfortable doing by now. We'll cross multiply and isolate, bring everything over to one side. Right? So we've got 400, take away 300x plus 50x squared equals 4x squared. We'll bring that over and subtract it, and we'll rewrite it in ax squared plus b plus c. So now from here, and again, depending on how comfortable you are mathematically, you have different ways of factoring. The goal is to determine the roots of the quadratic equation. So we're still trying to solve for x. I can't rearrange that. I'm not going to try and factor it at this point. I'll use the quadratic equation, but if you're comfortable doing that and breaking it down into its two roots, you're more than welcome to do that. So for the quadratic equation, we have x is equal to negative b, and you can refer back to the slide for that. So we've got negative 300 in this case, plus or minus the square root of negative 300 squared, take away 4 times a times c, all over 2 times the value of a. So it's a lot of work, but when we break that down, okay, you can use either your calculator, which has a program in it to determine what the roots are, or you can solve it by hand. We'll get 4.65 for our first root and 1.87 for our second root. So now we have to decide which one works for us. So if I look at this x, right, x is going to be subtracted. In the table here, the first column, the equilibrium concentration is 4 minus x. So if we used x minus 1, we'd get a negative value for concentration. So we can't do that. So we say that that is inadmissible, right? It would result in negative concentration. So our answer is 2. Okay, that's what x is equal to. The value is 1.87. So lastly, we'll sub that back in. Right, and we're asked to find the concentration of hydrogen iodide here. Right, we're not asked for the others, but we could solve for them. Right, we would just sub x in. So the concentration of HI is equal to 2x in this case, which is equal to 2 times 1.87, which equals 3.74. And I'll put the units at the end here, moles per liter. Okay, so that's our final answer based on what we asked. We were asked. We used an ICE table. We didn't have enough information, so we substituted it into K. We couldn't solve for it, so we used the quadratic equation to help simplify that. Right. So, moving forward here. There is a way to potentially avoid the quadratic equation. Right, so we'll do an example with that, and it's called the 100 rule. So very simply, if K is a very small number, that means very little product will form, and there's going to be small changes to the concentration of the reactants. So we can make the following assumption. If the smallest concentration, the smallest initial concentration, divided by K is greater than 500, we can ignore the change of x. Right? And what the change of x is when we say plus or minus x, whatever the value is. By doing that, we eliminate any kind of polynomial that can form because we're not expanding out an exponent. Okay, so we'll make a note of this. Concentration divided by K is greater than 500. Then it means to ignore x. So an example to go with that. I'll go to the Word document here. So given this, calculate the concentrations at equilibrium. So again, that means use an ICE table. Right? If you don't have enough information, go to your K value. So looking at this here, we'll just kind of split these up. I, C, and E. Okay, we've got that there, and the checkerboard is fine enough. We have a K value of 6.4 times 10 to the negative 7 at 2000 degrees. Remember that this doesn't factor in. Okay. We're going to use, oh, I didn't give you the concentration here, so we just got to leave it. It should say 1.0 liter container. Right. So very simple. 0.25 divided by 1 is itself. So our concentration of carbon dioxide initially is 0.25. We have no products. Okay. We lose our reactants. We gain our products, right? And the number comes from their coefficient in the equation. So for this, I'm just going to zoom in here, give myself a little bit more room. 250, take away 2x, 2x, and x. So I'm left with an algebraic expression for my equilibrium row, which means substitute that into K. So we've got the products, and they're all gases. We'll do a quick check there, over the reactants. Okay, and again, raised to their coefficients. So when we substitute in our equation here, what we notice is we're going to get a very complex term, actually. 2x squared times x. You might see that it's starting to be cubic function. 0.250, take away 2x, and that will be squared in this case. So we have a fairly complex scenario forming, right? So what we need to do here is rearrange this. So what we'll say here is this is where the 100 rule applies. Right? There's a reason that it's 500, but we'll keep that story for another time. So the concentration that we have is 0.250 moles per liter divided by the K value. Okay, this is our check to see how big this value actually is. And it works out to be approximately 391,000. So this is greater than 500, which means K is very small. Little product is going to form, and we can ignore the change of x. I'm going to use a different color to highlight this. Change of x. This is the change of x in this case. All right, so that concentration, the reactant, is going to change very little, so we can assume that when we round it, it's back at its original value. And we've incorporated a 5% error into this by saying 500, and that's why it's a little bit different. So really what happens now is we ignore this. Okay, we can't ignore the other x's because then their concentrations wouldn't be anything. We're just simplifying it out. So what we're left with here, right, and I will simplify this, right? 4x squared times x will be 4x cubed over 0.250 squared. Right? And then we can substitute that value back in now. So going from there, right, we can simply solve for x now. And it's easy to take a cubic root. And we don't have to do a cubic function, or we don't have to factor a cubic function. Instead, we can just solve for the variable simply. So if I cross multiply and then isolate for x, I've got 0.25 squared times 6.4 times 10 to the negative 7. We've got 4 times 10 to the negative 8 equals 4x cubed. Right, I'll bring the 4 over, divide that by 4, just to show a few steps here. 1 times 10 to the here. And then we'll take the cubed root of that function, and we'll find out that x equals 2.15 times 10 to the negative 3. Right. So now that we have x itself, right, it's very simple. We just plug it back in. Right, which is at the top here, and we can figure out what all the concentrations are. So I'll just put that here. I'll say, therefore, the concentration of CO2 is equal to 0.25 minus 2x, 0.25 minus 2, 2.15 times 10 to the negative 3. There's that value there. So we've got our answer times 2 and 0.25 0.25, take away that answer. And you can see that this is 0.246, which is very close to what it was. And if we were rounding to two significant digits, we'd have the same answer. So the concentration of carbon monoxide is going to be 2x, which will be equal to 4.3 times 10 to the negative 3 moles per liter. And then the concentration of oxygen is equal to x, so 2.15 times 10 to the negative 3. So there's the entire process there. By using the 100 rule, it allowed us to substitute out a complex equation that would have been difficult to solve even further than the quadratic equation. And remember, as long as that value is greater than 500, you can ignore the plus or minus x terms in the equation and then solve a bit more simply. So there's some good practice questions with this lined up here. Hopefully that helped clarify, and you can rewatch A or B as needed.